Imagine standing in your backyard with the most powerful drill ever invented. It's strong enough to cut through rock, metal, and even molten iron. You press the switch and aim straight down, determined to bore a tunnel that runs from your location to the exact opposite side of the planet. What would really happen if you drilled a hole all the way through Earth, from one side to the other, and then decided to jump in? It's one of those questions that sounds like a fun science fiction daydream, but exploring it reveals just how extraordinary and hostile our planet's interior really is. Your journey begins with the crust, the thin skin of solid rock we live on. Beneath your feet, the crust averages about 30 to 40 kilometers thick on continents and only about 5 to 10 kilometers beneath the oceans. Drilling an oil well a few kilometers deep is already a major engineering feat, and the deepest man-made hole, the Kola superdeep borehole in Russia, only reached about 12 kilometers before extreme heat and pressure made progress nearly impossible. But let's imagine your magical drill ignores such limits. You cut through granite, basalt, and the ancient rocks of Earth's crust until you reach the mantle. The mantle makes up most of Earth's volume. It's a vast region of semi-solid rock that slowly flows over geologic time, like very stiff putty. Temperatures climb quickly, from a few hundred degrees Celsius near the top to over 3,000 degrees near the bottom. As you descend, the pressure rises to hundreds of thousands of atmospheres. Ordinary drills and human bodies would be crushed long before this point, but our thought experiment lets you continue. You pass areas where convection currents churn, driving the movement of tectonic plates far above. Diamonds form in these depths, squeezed by unbelievable forces. The heat becomes so intense that the walls of your tunnel glow cherry red, and molten rock tries to flow inward the moment you remove material. After roughly 2,900 kilometers, you reach the outer core. Here the material isn't rock at all but a sea of molten iron and nickel, conducting electricity and generating Earth's magnetic field. Temperatures hover around 4,000 to 5,000 degrees Celsius. The pressure is so immense that the iron behaves more like an incredibly dense liquid than the metals we know on the surface. Drilling through this layer would be like boring through a star. Any real tunnel would collapse instantly as the surrounding metal flowed to fill it. Even in our fantasy scenario, the heat is almost beyond imagination, hotter than the surface of the sun. At about 5,100 kilometers down, you finally reach the inner core, a sphere of solid iron and nickel nearly 1,200 kilometers thick. Despite temperatures around 5,500 degrees Celsius, the pressure is so high that the metal remains solid. Seismic studies tell us it may rotate slightly faster than the rest of the planet. Here, gravity behaves in a surprising way. As you drill deeper past the halfway point, the pull of all the surrounding layers begins to cancel itself out. Near the very center of Earth, you would feel weightless. Gravity from the overlying rock pulls equally in every direction. From the center you begin the long climb, still drilling, through the mirror image of what you just crossed. Inner core back to outer core, then mantle, then crust, until finally your drill breaks through to the opposite side of the planet. If you started somewhere in the United States, you'd probably emerge in the Indian Ocean. Most land locations have antipodes in open water. The tunnel is finished. It's a perfectly straight shaft from one side of Earth to the other, magically reinforced so it doesn't collapse and somehow kept free of the unimaginable heat and molten metal pressing in. Now comes the next question everyone asks. What if you jumped in? You leap into the hole. At first it feels like a normal skydive. Gravity pulls you toward the center, and you accelerate rapidly. With no air resistance you'd pick up speed fast, about 9.8 meters per second squared. After a few minutes you'd be falling thousands of kilometers an hour, far faster than any spacecraft in low Earth orbit. As you approach the planet's center, something fascinating happens. Gravity weakens. The layers of rock and metal above you begin to pull in every direction, canceling out the downward tug. Your speed continues to carry you forward, but you feel lighter and lighter until, at the very center, you're briefly weightless. But your momentum doesn't stop. You keep moving toward the opposite side, slowing as Earth's gravity now acts against you. The pull of the center is now behind you, trying to drag you back. Your speed drops until you reach the surface on the far side at exactly zero velocity, like a perfectly timed swing of a pendulum. If there were no air to slow you down, you would simply oscillate, falling back, then forward again, taking about 42 minutes to travel from one side of Earth to the other each way. It would be an endless, back and forth journey through the planet's core, like riding a cosmic elevator. Of course, reality is less forgiving. If your tunnel contained air, you'd quickly run into air resistance. The friction would heat the air until it glowed, and you'd reach a maximum speed of only a few hundred kilometers per hour before drag slowed you down. You'd never make it to the far side. Instead, you'd come to rest somewhere near the center after a long, hot, suffocating ride. Then there's the small matter of the core's temperature. Without a hypothetical cooling system, the air inside the tunnel would be hotter than a blast furnace. Any real traveler, or even the walls of the tunnel, would be incinerated. Even with magic materials, a through-Earth tunnel faces impossible engineering problems. The crust is constantly shifting with earthquakes and plate tectonics. The mantle flows, slowly but relentlessly. The outer core is liquid metal under incredible pressure that would squeeze inward the moment the drill bit stopped. No known material can withstand those forces. Suppose you tried to fill the tunnel with a vacuum to avoid air resistance. You'd need massive doors at each end to keep the atmosphere out, and those doors would have to withstand the full weight of Earth's air pressing on them, over 1,000 tons per square meter. Keeping the entire shaft perfectly sealed and aligned through a spinning, shifting planet is beyond any technology we can imagine. Still, the thought experiment leads to some fun possibilities. With a frictionless vacuum tunnel, you could create the ultimate transport system. A capsule could be dropped into the shaft and simply oscillate like a pendulum, reaching the other side in just over 40 minutes without burning fuel. Magnetic systems could catch and release the capsule at either end, making it a kind of gravitational subway. In theory, this would be the fastest way to travel between two antipodal points on Earth. Another mind-bending detail. Earth's rotation means that if you jumped in from a point not on the equator, you'd also have sideways motion. Because the planet is spinning, the walls of the tunnel wouldn't remain perfectly lined up with your path. Without guidance, you'd crash into the side long before reaching the center. A safe ride would require a carefully engineered capsule with its own stabilizing thrusters. What we learn from the idea while we'll never dig such a tunnel, thinking about it teaches us a lot about our planet. We understand the layered structure of the crust, mantle, and core not from direct observation. No one has been farther than a few kilometers, but from seismic waves generated by earthquakes. They reveal how density, temperature, and composition change with depth. The idea also highlights the delicate balance of Earth's interior. The molten outer core drives the magnetic field that shields us from harmful solar radiation. The slow convection of the mantle recycles carbon and other elements, regulating the climate over eons. Our planet's deep interior isn't just a barrier to drilling, it's the engine that makes life on the surface possible. So, what if you drilled a hole all the way through Earth and jumped in? With a magical drill and impossible materials, you'd enjoy a gravity-powered ride that takes you from one side of the planet to the other in under an hour, oscillating back and forth like a giant pendulum. In reality, though, you'd face crushing pressures, searing heat, liquid metal, and shifting rock that would seal the tunnel almost the instant you made it. The deepest hole humans have ever dug barely scratches the crust, and for good reason. Our planet's interior is as hostile as the surface of a star. The fantasy may stay in science fiction, but it offers a powerful reminder of the incredible forces hidden beneath our feet, and of how thin and fragile the surface world we call home really is.